the title of which is From 50 Plus Quantum Optimization Use Cases to Scalable Industrial Impact in the Real World. By the way, GZEP is a Japan-based quantum software company pioneering the real-world application of optimization technology across diverse industries. So if you want to go check that out, I encourage you to. Our next panel is going to be a discussion titled Quantum Hardware Pathways from Photonics to Diamond and Beyond. And I want to invite our panelists to come up. Dr. Mark Mattingley-Scott, General Manager EMEA at Quantum Brilliance. Adam Hammond, Business Leader, IBM Quantum Sales in EMEA. Max Al-Hasso, Research Engineer at Quantum Dice. And the panel will be moderated by Dr. Siti Fariya. She's Research Associate at Herriotwat University. So, lady and gentlemen. Got the seating sorted out. Seating, everyone got a mic. Put the little coffee table in between so you can put your cocktail there. Oh no, it's too early for that. Water is enough, yeah. Anybody need water while I'm here? You good? All right. Yeah. Let's give them a hand just so we know that we're glad they're here.
Check. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Actually, afternoon. So it's a very pleasure for me to be here to moderating this session together with these three gentlemen here. And today we're gonna talk about the quantum hardware pathways from the photonics to the diamond and beyond. And we would like to explore what the progress that has been made and also what's the challenge that remains. And we want to gain more knowledge as well, how this kind of technology can be applied into real case scenario, especially in the maritime area. So before we start our conversations, I would like to invite our panelists to introduce themselves and also maybe a little bit information about what they are working in terms of quantum hardware. May I start with Adam, please?
Hi, so I'm Adam Hammond, and I lead IBM's quantum business for the Europe, Middle East, and Africa. And basically, I spend my days talking to clients, talking to universities, and exploring the use cases that hopefully will get industry started and drive the value for the industry.
Great. And we can also jump into Dr. Mark, please.
Yeah, my name's Mark Mattingley-Scott. I do more or less the same as he does. But I also spend a lot of time talking to investors and answering the question or sketching pathways for customers to answer the question of when is quantum computing, quantum sensing actually going to provide a commercial value, and what will that mean, and what will that look like? We had a preview of that with the distinguished speaker, the Swiss speaker with his cheese and his chocolate. That was a taste of what's to come. It's going to be a fundamentally disruptive technology. So it's my job to explain it.
Great, exciting. So the next is Max Al-Hasso from Oxford Quantum Dice. Please introduce yourself.
Yeah, hello, I'm Max Al-Hasso. I am a research engineer at Quantum Dice, and we produce quantum random number generators based on photonics, and then we apply those to accelerating randomized algorithms. So slightly separate to quantum computing, but still a quantum technology nonetheless.
Amazing. So thank you very much for all the panelists for the introductions. So let's start the discussion with the comparative hardware pathways. So probably the first question is going to be for Adam again. So may I ask a question from the IBM perspective? How do you see the state of quantum hardware development, particularly in terms of the milestone that has been reached, and then with the superconducting and also hybrid approach? So what's your opinion?
So I think firstly, it's really important to recognise where we've come from in the last few years. So I was just actually looking back at what we've done. In 2021, we announced the world's first 100 plus qubit chip. We made it available on the cloud for people to use in 2022. In 2023, we published a paper in Nature that demonstrated that this machine could actually do not very useful problems, but it could do something that goes beyond what you could just simulate on a classical computer. And in doing that, we demonstrated that things like error mitigation techniques, where you use classical techniques to clean up your data and get rid of the errors, actually work. Also that year, we launched our next 100 plus qubit chip, the Heron, which is now our workhorse chip. And actually, we're on version 3 of the Heron chip today. And that's all in, well, if you think about when the first 100 qubit chip was actually on the cloud, it was in 2022. So in 3 years, we've come that, we've gone from essentially machines that were dealing with toy problems to machines that can actually act as real research tools, albeit not yet at a production scale, but that can actually help scientists and researchers solve real problems. At the same time, we've also seen real advances in algorithms. So, for example, the work on SQD in chemistry, which is starting to bring, again, real problems within reach. So I think sometimes we forget how fast things are moving and how quickly we've managed to achieve what we're doing. And obviously, I'm talking for IBM, but I think you could probably make the same claims for most of the hardware companies in the industry. So I think the really important thing is we're now at a stage where quantum computers are useful for doing research into real problems and really starting to prepare for some kind of production. And I think this sort of culminated in, you may have seen the paper we jointly published with HSBC 2 weeks ago. And this is a really good example of a company that we've been working with for 5 years. And as the hardware's progressed and as the approaches to dealing with algorithms have progressed, we're now at a stage where, doing something useful feels within reach.
Amazing, fantastic to hear about the progress of ABM Quantum. Yeah, we see a lot of things is happening now, right? So for Max, as a research engineer at Quantum Dice, I guess your work is really touched directly on the photonic and secure quantum system, right? And what is the milestone in photonic quantum technology that you think it is very important for today's?
Yeah, certainly. So I think for quantum dice in particular, I think it's sort of the miniaturization of this technology that we've been working on. So what was originally like a workbench scale random number generator is now a PIC, a photonic integrated chip, and is on like the millimeter scale. So within fewer than 5 years, we've moved from that sort of more experimental system to something that is manufacturable. I think kind of that is probably one of the major breakthroughs for photonics as it relates to QRNGs. Yeah.
Yeah, amazing. So photonic quantum is also moving forward quickly, I guess. Yeah.
Yes. Yeah.
Yeah, fantastic. So for Dr. Mark, please, quantum brilliance is advancing diamond-based system, right? And what do you see actually as the key achievement in this field, and how do they position diamond as a credible way for this hardware? If you could explain, please.
Yeah, sure. I think if we look back at the history of the semiconductor revolution, which began in the 50s and the 60s. What we now have, I have a device on my wrist which has, I think, about 12 billion transistors on it, and I can knock it and do this sort of thing with it. The long-term race goes to the most scalable technology. Our objective with diamond and nitrogen vacancies, we have a technology which works at room temperature, which is mechanically robust and can be produced, and this is a unique unique thing that quantum brilliance is doing can be produced in a deterministic manner, so we can build a manufacturing process around it. So I think that's going to be a very important direction for quantum computing, quantum sensing as well. I think a future without IBM is equally unthinkable. I think there will be a market for both. I'm convinced that, of course, that the diamond market is going to be significantly bigger than IBM's, but we'll see. I still love IBM. I worked there for 32 years, so anything else would be heresy. I think the interesting thing for where we are today is what would be a deployment scenario for logistics for the maritime industry. If you can shave off 1% of your time to decide which container to position on which vehicle, if you could shave 1% off those kind of metrics, the savings would be in the tens of millions per year. The finance industry has a similar problem, but there the numbers have a few more zeros. And that's why each of these industries is very focused on quantum computing, because you only need to make a very small improvement to be better. So imagine a world in which we have a quantum computer or qubits, perhaps in the size of one of these tissue boxes here at the front, and I have a couple of hundred qubits in there at room temperature, so there's no cooling, there's none of that. And I put one of those every 100 meters on the Abu Dhabi port, and have them running some optimization or some scheduling or something else that's relevant and important. I don't know the details of the use case, but I'm sure with that kind of power there'll be a massive impact. So it's very interesting to see that connection. Obviously, Dubai, Abu Dhabi, lots of big ports in the Gulf. Singapore, other big ports. We're talking to all these other ports. So I'm keen to get into dialogue and talk about that.
Great. Yeah, thank you very much for all the panelists. Really give us a rich view across the three different hardware, but it's still complementary to each other. So it's very good, actually. And moving forward, I want to talk about scalability challenge. So a question for Adam again, please. So I believe scaling of quantum system is the central of IBM roadmap. And what do you think about the engineering or error correction strategies in terms of IBM quantum hardware?
So we published an updated roadmap this summer. So last year we published a paper in Nature again, which introduced a new approach to error correcting code. Essentially what it means is that it's 288 physical qubits to give us 2 logical qubits. That dramatically reduces the hardware requirements to actually produce a machine that you can do something useful with. And that's really what it's all about. As part of that roadmap, we published a very clear, and Ahmed talked about it yesterday, we published a very clear path that says we know what we need to do. There are absolutely some engineering challenges to do it, but we're very confident that in the lab we're going to have our Starling fault-tolerant machine complete by 2028 and available for people to use by 2029. The challenge we see is on the software side. It's the applications and algorithms. And I think it's very clear today that if we were to magic up, a 200 qubit logical qubit machine today, people wouldn't know what to do with it. And this is why we need to engage with, the maritime industry, the financial services industry, because it's all about business value. It's all about generating a return. We've had the machines really for sort of 2 years. Hardware's been doing great. what we need to do is we need to get the same focus on the algorithms and applications so that we can actually apply these to real customer problems. So I'm very confident about the hardware roadmap. And, you know, many of our partners, many people we partner with are in the room today. You know, it's the ecosystem, it's all of us working together to actually deliver the value now that we have the hardware.
Okay, so it's more like the algorithm and case study itself rather than the hardware. Brilliant. So, Dr. Mark, what about you? Like, what do you think? What is the biggest challenge in terms of scaling the diamond-based quantum computer hardware?
We know from extensive simulations that we've done that 200 noisy qubits, or NISQ qubits, in a combination of a combination with a GPU, so it's a GPU-QPU combination with 200 qubits, noisy qubits. We could significantly increase the accuracy of voice recognition with arbitrary speaker in a noisy environment. Arbitrary speaker in a noisy environment, that's an ambulance, that's a pilot in a helicopter, there's lots of scenarios. 200 qubits is, however, big. If we can get to 200 qubits, noisy qubits, with Diamond, and we can actually use them, then that would be a scalable, in the commercial sense, a very scalable solution. In terms of the number of qubits, nitrogen vacancies in Diamond were historically made by implantation, which is a non-deterministic process. You basically fire nitrogen atoms at a diamond, and then afterwards you go and look and hope you've got some qubits. And sometimes you might need to look for 6 months to find a qubit. What we're focusing on is building that deterministic process, and then the scalability of the qubits is if you can deterministically place them, it's then a question of yield. Yield is a term from the semiconductor industry. Most people here will understand it. Once you create demand and volume, then yield always goes down, always goes up. So there's two things playing there. I'm very confident that both will yield. Sorry for the bad joke. Both will yield interesting commercial pressure and interesting commercial flow. On the topic of error-corrected qubits, which is where a significant proportion of the industry is transferring their focus because of the challenges of using NISQ qubits. Obviously, for us, that's also a topic. But again, the kind of error correction you do with a Josephson junction is quite different from the kind of error correction you would do with a nitrogen vacancy or with photons. So there's a lot of work to be done there, and I'd share Adam's view about the algorithms. We know that qubits are good at solving complex probability distributions. That's what they are. How do you translate that into things out in the real world? There's still a lot of intellectual work to get our heads around that.
Great, fantastic. It's good to hear about the progress in terms of diamond hardware as well. Yeah, it's very interesting for me. So next is Max. How about the photonics quantum? What is the main challenge for the scalability, and how will you overcome that challenge as well?
Yeah, so I think with respect to quantum computing, I echo what the two other panelists have said. I think it's important to realize that photonics itself is not a monolith. There's like different materials within photonics that can be used. So you have indium phosphide or you have silicon, both of which are like very different processes. And yeah, so we have that. But I think with scalability, at least the issues that I've seen are probably more to do with sort of the size of the talent pool of people who can work with photonics. And then also there's only very few foundries in the world that can like manufacture photonic chips currently. So I think as those two things increase, we'll probably see a larger adoption of photonic chips and scalability of that hardware. Yeah.
Amazing. So it's really promising, like all of the quantum hardware. Like I know it's quite like a different approach, but yeah, it's really promising for three of you. So yeah, well done for everyone. And moving forward, I want to talk in the way of clear applications. So would you like to explain in a clear way, like what we can do to handle maritime application with your hardware? Maybe it's the same question for the alt panelists, so I can start with Dr. Mark, please.
Yeah. So a couple of years ago, we did a study on what might that look like in the particular case of if I had a small, maybe 100 qubits at the edge, in an edge deployable scenario, what would that look like in the maritime environment, or what would that look like in a port? There are lots of interesting use cases. The challenge you will always have in a port. Port is a very tightly run commercial enterprise. It's about volume, and that's about managing costs. A quantum computer is not going to do anything useful at the moment for a port. However, if I look at, for example, I think Singapore has 200 berths. I think in Abu Dhabi you have around 40 in total, if I remember correctly. I remember that in Singapore there was the limit of, it is completely automated, the entire system is automated. The limit of the capability to plan and schedule was a very small subset of those 200 berths. With quantum computing, the question is then can you extend that? Could you manage the entire 50 kilometers, I think it is, of berth front in Singapore? Can you manage that together? And we can't really say because we haven't got the systems, but there's some very encouraging indications that problems that today are completely unthinkable, untractable, will be solvable. And again, it's about the 1%. Find the first small 1% use case, which actually has a business benefit, and turn the money machine and invest all that saved money in quantum brilliance and IBM and others.
Yeah, amazing. So yeah, I will take that note, like find a little 1% study case, then show the benefit, right? Then we can move forward to the bigger case. Yeah, amazing. So I would love to hear about the IBM, please.
So the maritime world is a microcosm of the bigger world. And if I look at some of the use cases and completely agree with Mark's comment about, find that small use case that generates a lot of value. And if I look at some of the things that we're doing, working with ExxonMobil about looking at things like routing, there are tons of optimization problems in the maritime industry. Everything from workforce scheduling to tanker routing to container management. There's also an awful lot of stuff that's going on in the financial industry that is equally applicable. So if I look at the paper we published with HSBC, if you translate that into things like fuel hedging, one of the largest costs for the industry is fuel. We're having similar conversations with the airline industry. And then if you look at the chemistry side, the work we're doing with Boeing on corrosion and surface chemistry, in fact, I would probably say more applicable to shipbuilding. Conversations we're having with shipbuilding companies about actually how do you optimize the placement of, the various assets that you put on a ship in order to, minimize fuel consumption, maximize economy, et cetera, et cetera. So I think the industry itself has lots of problems. I think what's really important, going back to Mark's point, is I think we're all very conscious as an industry that we've been talking about quantum is coming for a very long time. We sort of need to demonstrate that it's more than just coming, that it's here or hereabouts. And so finding these small, doable problems that are, that are doable on today's hardware or maybe on tomorrow's hardware, and demonstrating that they can deliver business value, to encourage people to actually get started, I think is really important, because I think, it is within touching distance, but we're only going to get there if we're actually going to do real stuff with real clients and solve real problems.
Brilliant. I also like the opinion that you say about we can learn from another area, for example, like routing in logistic, right? Because it's also related to the optimization in the maritime, and also the chemistry one. Is it very related to shipbuilding? Because yeah, definitely corrosion and everything is there, right? So yeah, brilliant. So next, I want to hear about the photonic quantum. Was there any maritime application before, Max?
Yeah, certainly. So I think this week we've spoken a lot about both secure communications and cryptography, as well as combinatorial optimization. And in two different ways, these QRNGs can be applied to those use cases. So if you have a high-speed certifiable QRNG, that is a good source of key material for post-quantum cryptography for secure communication at sea. We saw, I think, in the ID Quantique demo where you could use the QKD across land, but then you still need to secure the communication across the sort of wireless part of the communication. So there's an application there. And then I think more on the combinatorial optimization side, these algorithms are typically heuristics, they're randomized algorithms. And so if you have some source of randomness that isn't deterministic hardware trying to generate that randomness, you can apply it in this method that we refer to as probabilistic computing, which Dr. Novoselov spoke about yesterday. And using this probabilistic computing method, we can accelerate those combinatorial optimization problems at maybe a sooner pace than the quantum computing applications that are coming and will be very valuable when they're here. But as a nearer term solution, you can use these randomized algorithms. So, yeah.
Yeah, fantastic. Yeah, I also heard about your talk yesterday as well about that combinatorial problem. So
Yeah.
that's great. So another question for all panelists again, it's about hybrid and future directions. So do you think this hybridization is just temporary, or no, this is the future? So it's not just temporary to fill the gap, but also we're gonna use this hybrid in the long way. So what do you think? We can start with Max, please.
Yeah, sure. So actually, Adam and I spoke about this yesterday a little bit, but I think the sort of my background is quantum algorithms and more on the theoretical side. And as a theorist, you're not so worried about what the hardware is because we're all working towards some sort of unified set of operations and some unified set of gates. So I think that, from my perspective, I think all of the hardwares will have their own advantages and areas where they're more applicable than others. Ultimately, for quantum computing, they'll all be producing sort of the same interface for the algorithm developers and the software developers of the future. Yeah.
Great. So what about Dr. Mark?
Back in the days of the very first microprocessors, a microprocessor had a program control unit, PCU, and an arithmetic control unit, processing unit, APU. And the APU was very good at doing algebra. So what happened was the world then turned its focus to translating every solution they could think of to every problem into an algebra, some kind of algebra. The last 15 years, the GPUs came along. Originally, they were designed to basically calculate the next frame of a game, of the picture of it in a game. It turns out they're very good at matrix algebra. And suddenly the entire world looks at all the problems in the world and is trying to find solutions which are basically matrix algebra. In the future, there will be a world with QPUs. QPUs are very, very good at solving complex probability distributions very, very efficiently. So we will see, and again, this comes back to the algorithm point, we will see a massive focus on what is there out there which can be solved by something which is very good and fast at solving complex probability distributions. If you look at all the existing algorithms, that's essentially what they do. The inverse consequence of that is that we have CPUs with APUs built in. We have GPUs. We will have QPUs. That's how it's going to be. That will be the world in 20 years. So yes, I think hybridization is, or hybrid computation is the way it is for quantum.
The way it is, yes, great. What about ABM perspective?
Well, so 100% agree with Mark. And QPU, I mean, and not to dismiss how important QPUs are. QPUs are another form of coprocessor that, as Mark says, solves certain types of mathematical problems, as he said, in the same way that GPUs do it. And I'm sure there will be other coprocessors that exist doing other things that are useful to do. I think so the answer is it has to be hybrid, because actually quantum processors can't do the orchestration. They can't do, the Turing machine kind of processes that we actually need to be able to do. You're not going to be able to write a spreadsheet using a quantum processor. You might use a quantum processor to solve a particular mathematical problem from within that spreadsheet, but that's essentially how it's going to work. And I think that's probably one of the biggest misconceptions I come across when I talk to clients. When can I put this whole problem on a quantum processor? Well, the answer is probably never. And in fact, to start with, it's probably only going to be a very, very tiny bit of the problem you're going to put on that. And over time, maybe more of the problem will become something that you can put on a quantum processor as we solve the maths and the algorithms, etc. But no, the world is hybrid, and it will carry on being hybrid.
Great. So I think everyone here is agree that hybrid is the future, not just like a temporary things to fill the gap. Brilliant. So we are finally coming to the last questions about the forward-looking questions. So may I ask, maybe in 5 years, what is the one of breakthrough in your pathway that you believe will accelerate the real-world application, especially in maritime? So I'm going to start with Adam again.
I could list a load of technical achievements. We've got fault tolerance coming. I'm sure we'll have improved algorithms. But actually, I think the one thing that will make a massive difference is the first client putting their hand in the air and saying, I've got a return on investment, in my business from using quantum compute. And that will be we talk a lot about what's our ChatGPT moment. That's the ChatGPT moment. I've talked to more financial services companies in the last 2 weeks since the HSBC paper than I have in the last 2 years. So it's all about business value, and I'm pretty sure that as soon as the first company puts their hand up and says, I've done something useful and earned money using a quantum computer, the rest of the world is going to pile in.
Amazing. I like that ChatGPT term. So yeah, I totally agree with that. Money will be the breakthrough. So what about Dr. Mark?
The first business case, essentially, that's going to focus the entire industry on that particular methodology and how that way of writing algorithms. We saw this 50 years ago with silicon. The very first piece of silicon with multiple transistors on it was a very specialized piece of hardware developed, I think, for Sanyo, a Japanese company, and it was a processing unit for a desktop mechanical calculator, which was an electromechanical calculator in 1960-something. Had 1,700 transistors on it. Shortly thereafter, we had the microprocessor. The rest is history. So we see that focus on the one business case. So that's going to be the killer app, the WhatsApp or the OpenAI or ChatGPT moment or the Turing moment. For quantum brilliance, in the 5-year timescale, we've contracted to produce 25/50 qubits on a mobile quantum computer for the German government. Mobile means literally the size maybe two of these tissue boxes, maybe three. I think once we've done that, then the sky's the limit. We'll be pushing for a very large number of qubits, and I'm sure there'll be other challenges. But for us, it's about getting onto the kickstarting that cycle of virtue.
Amazing. So more qubit and also mobile quantum computing.
Very definitely.
Yeah. So what about photonic quantum, Max?
Yeah, I think I fully agree on the business use case point of view, but for a more technical comment on a breakthrough in photonics, I think that the ability to co-design a chip that has both silicon photonics and also conventional CMOS standard electronics will be a really meaningful breakthrough, or at least making this more readily available, because this will just allow adoption of this technology to increase. Currently, it's too expensive to prototype and to manufacture without this kind of more like succinct process. So figuring that out from a technical perspective, I think will add a lot to the photonics side of the hardware.
Amazing. So yeah, so we are already finished with all the question, and thank you very much with the talk. It's very interesting and really gain our knowledge about the pathway to the quantum hardware. Because the time is very limited now, I would like to just have one question from the audience, please. If there is any question to the panels, you are very welcome.
Question? Somebody had a question? I'm going to query him now. No, me speaking in the mic. So a question about the quantum brilliance. So again, a unique perspective, right? Nitrogen vacancy. So can you speak more about the device that's the size of 2 Kleenex boxes that's
Maybe it's
being
three.
used at a bank? You know, anonymized white label. You don't have to tell me the bank, but just what are they doing with it?
I can't really tell you details.
Okay.
It's the German cyber agency. You can join the dots. But the requirement. So it's quantum brilliance with a company called Parity QC from Innsbruck in Austria. We're in a consortium together. And there are 2 other consortia currently. So this phase is to build 25 qubits. With a volume of less than 1 cubic meter and a weight of less than, I think, 800 kilos. Those numbers are set because the 2 other technologies are ion traps. And to make ion traps, you need lots of hardware and infrastructure and stuff and lasers. On the size and the power, less than a kilowatt power consumption. So our development kit consumes just over 100 watts. It weighs a few kilos. The hardware we're currently working on will weigh a couple of kilos. I mean, it might be 10 kilos or it might be 5. Don't quote me on that. But it'll be portable.
Yeah. They're rack-mountable devices, aren't they?
Yes. So we have 5 rack-mounted machines out there in the wild. 1 is in Freiburg in Germany. 3 are in Oak Ridge National Labs in the Supercomputer Center. And 1 is in the Pawsey Supercompute Center. And interestingly, we install those and they work in I don't know if any of you here work with high-performance compute or compute centers. They are extremely aggressive environments. The noise levels are very high. There's a loss of vibration that's normally death to qubits. But we're doing well.
Thank you. Other questions? Anyone want to query the panel? Here's your chance. No? Okay, well, how about giving them a hand? Thank you, Siti, Adam, Mark, and Max. Okay. So it's time for lunch.